right, so example 9.3.1. So a hypothesis test for two means. So the cholesterol level of patients who had heart attacks was measured 2 days after the heart attack. The researchers want to see if patients who have heart attacks have higher cholesterol levels over healthy people. So they also measure the cholesterol level of healthy adults who show no signs of heart disease. Okay, the data is given below in the table. So do the data show that people who have had heart attacks have higher cholesterol levels over patients that have not had heart attacks? And we're told to test at the 1% level. So that gives us an alpha value of 0.01. All right, so the first thing that we would do is we would need to either upload these two lists of data to StatCrunch or to input those two data sets into our calculator. So list 1 and list 2, or to use StatCrunch. Okay, and in this case, we do not compute a difference list. Okay, these are not paired data. All right, so in this case, these patients that had heart attacks are different from the patients who are healthy. So it's not the same individual in both groups. So it's not like we took some patient and made him have a heart attack and then somehow miraculously made them a healthy individual for the other measurement. So these are not two measurements taken on the same individual. And it doesn't say anything in the paragraph where they have matched one to another based on like exercise level, gender, age, other things that might affect cholesterol level. And a clear indication that they must be independent is also the fact that the data sets are not the same size. So in this case, they cannot be paired. So in this case, even if you tried to compute a difference list, you're going to get an error message on your calculator because it's not going to know what to do with these last two spots where there's nothing here and there's a 200 on the other side. All right, so for the hypothesis test, again, we're going to walk through the steps for phantoms. So again, the first one is the parameters. So in this case, mu1, doesn't matter which group. I'm just going to take the first group they talked about, which is the heart attack patients. So this is going to be the mean cholesterol level of all patients who had a heart attack. And group 2 is going to be the healthy ones, so this is going to be the mean cholesterol level of all healthy patients. Okay, we do not know what those parameter values are, so we're going to get information out of the random variables that we take from collecting sample data. So X bar 1 is going to be the mean cholesterol level of 28 randomly selected patients who had a heart attack. And because again, in that first list of data there were 28. In the second list of data there were 30. So this is going to be 30 randomly selected healthy patients. All right, so the H now is to set up the hypotheses. So H sub 0, H sub A. We have quantitative data, so we're going to be dealing with means, and they're independent groups. So we've got mu1 equals mu2 for our null hypothesis. And for the alternative, it said that we wanted to test that those that had, so again, remember this is our heart attack group, and group 2 was our healthy group. And we wanted to test that the heart attack group had a bigger cholesterol level. So we want mu1 greater than mu2. And in this case, they gave us an alpha value of 0.01. All right, so A, we need to check our assumptions. So again, for all of these tests, we're going to assume we took some random samples. So a random sample of 28 cholesterol levels of patients who had had a heart attack is taken, and a random sample of 30 cholesterol levels of healthy individuals was taken. Okay, the second one, we need to have independent samples. So in this case, the patients in group 1, okay, were not matched or paired with the patients in group 2. So these are independent samples. All right, the next condition is that, and again, it's a double whammy because now we have 2 independent groups, so we have to check these conditions on each set of data. So we either need to be reasonable to assume we had a normal population, or we need a sample size of at least 30 and no outliers. So if we start with the patients who had heart attacks and we look at that histogram, it looks somewhat bell-shaped. Okay, so the histogram is roughly bell-shaped. Again, it's kind of hard to determine shape with small samples, okay, but it looks pretty good. And we go then and use our modified box plot to check for outliers. So our modified box plot here shows no outliers. And if we look at the normal probability plot, and again, StatCrunch calls that a QQ plot. Okay, but the normal probability plot for those cholesterol levels looks somewhat linear. So again, it's roughly linear. Again, so the points in here are staying fairly close to this line. Again, we've got a few that look like they're getting further away. So again, StatCrunch doesn't put these confidence interval bands on these types of graphs, but within here those bands allow us, we want it to be fairly close to the line in the center, and it is allowed to wander a little bit more in the ends. And we know from the previous graph up above that there are no outliers in there. So in this case, we're going to say it is reasonable to assume that the population of all cholesterol levels, and again, in this case we were looking at the patients who had heart attacks, is normally distributed. Okay, but that's only half of it. We've got the other group of data that we need to look at as well. So now if we're looking at the healthy individuals, okay, here's our histogram, which does not look bell-shaped. So it does not look bell-shaped. Our modified box plot shows no outliers, so no outliers, which is good. And if we look at the normal probability plot, again, it looks pretty linear, but again, it's starting to kind of wander here and kind of wandering off down on the other end here. So in here, looks roughly linear. But in this case, even if we were to question that, this particular set of data, and actually the other one's pretty close to 30, but at least this one we did have a sample size of at least 30. So the sample size for this group is 30. Okay, so sample size is greater than or equal to 30. And there were no outliers. Okay, so it's reasonable to assume that this set we can also proceed. Okay. So our last condition is we need the population standard deviation has to be unknown for each group. So again, sigma 1. All right, so touch screen went wacky for a second. So sigma 1 and sigma 2 are not given. And again, they cannot be computed from sample data. Now, we could input the data and we could get a value for S1 and S2 for the sample standard deviations, but this says the population standard deviations are unknown, which they are. So in this case, everything checks out to run a 2-sample t-test. All right, so on the TI-84, we would hit Stat and arrow over to the Test menu and scroll until we find the 2-sample t-test. And in this case, we have data, which we entered into L1 and L2. Again, the frequency 1, frequency 2, those default are 1, and we never touch those all semester long. And in this case, our alternative hypothesis, we wanted to test that mu1 was bigger than mu2, so we'd highlight the greater than mu2 symbol here. All right, now in this level of course we're not going to get into when we would do something called pooling variances versus not. So for this intro course, next to pooled, this should be highlighted as no, and again, we're never going to change that in this intro course. Okay, so then we can scroll down and highlight calculate and hit enter, and then the output screen, again, before we look at any of the values, you just need to double check that your alternative hypothesis that you've written looks like the top line of the output screen. So mu1 greater than mu2, so that checks out. And then again, we have our t-score, so there's our test statistic, where it says p is really our p-value. And then again, here we've got our sample statistics, x bar 1 and x bar 2. And again, we can also use StatCrunch to get those values as well. All right, so no matter what technology you use, we're going to get the following. So in this case, on the TI-84 calculator, it gives us x bar 1 and x bar 2 separately, and we would need to subtract them ourselves to get this difference. Okay, in StatCrunch, it actually computes that difference for you. So if we were to subtract these two numbers, we would get 60.795238. And quantitative data, so these things get units. And then our standardized score, so our test statistic here, we're going to take that difference that we observed, and to really see how big that difference is, we're going to divide that by standard deviation. And so S sub 1 squared, so we're going to take, again, and those, if we scroll down on the screen, we would see the other ones here. So this would be 47.7104916 squared over the sample size, which is 28, plus the other sample standard deviation is 22.3000438 squared. And that is over a sample size of 30. So again, we're not going to actually run through that key punching. We can, again, we're going to just cheat and take that test statistic right off of our technology. So again, whether you use a calculator or StatCrunch, either way, this is about 6.15. Okay. So these last few steps in Phantom. So obtaining the p-value. So on the TI-84 screen, we see that that is about 1.86 times 10 to the negative 7. And on StatCrunch, when it's so small, it doesn't use scientific notation. It just tells us that p-value is less than 0.001. Okay, so basically less than any reasonable alpha value that we would use in this class. So again, as we draw out a picture about what that means, so again, our statistic was x bar 1 minus x bar 2, and the standardized test statistic was t. The claim is true. Both of these would be centered at 0. The actual difference we saw was 60.8, and the corresponding t-score to that was 6.15. This is a right tail test, so that p-value is going to be the area in the right tail. Okay, so if we rewrite this, again, we would push this decimal place back 7 times to the left, which would put 6 zeros out in front here before the 186. So rounded off, we get the p-value that's given here. And again, our level of significance here was 0.01, so this p-value, teeny, teeny, tiny. So definitely less than or equal to 0.01. So since p-value is less than or equal to 0.01, we would reject H0. And so again, if we reject H0, that means that what we want to write in context here is that mu1 is bigger than mu2. And so whenever we reject HO, our conclusion is going to start out, there is significant evidence to conclude. And then we're just translating mu1 greater than mu2 all back into words. So if we flip back a few pages to where we first defined these parameters, mu1, to conclude that mu1 was the mean cholesterol level of all patients who had a heart attack. So again, all, not just the 28 in our study. And then greater than, so is greater than or higher than. And then mu2, in the context of the problem, was the mean cholesterol level of all healthy patients. So when we say all, we're not talking about just the 30 in the study. We're talking about all of them. So for this area, whether that's, a few thousand, a few 100,000 patients, again, the all, we're looking back to the entire population, not just those in the sample.